Hello and welcome to the poster presentation of LucidProts, controlled protein design using diffusion language models. My name is Adrian Henkel, and this poster covers the result of my master's thesis that I'm currently writing at the Technical University of Munich at the Rost Lab, where I'm supervised by Michael Heinzinger, Gira Erkert, and Burkhard Rost. In this work, we provide a proof of concept on how diffusion language models can be applied on the problem of inverse protein folding. Recently, generative models such as DALL-E, Imagen, and Midjourney have gained a lot of attention because they generate high-resolution images conditioned on a text prompt using so-called denoising diffusion probabilistic models. In this work, we used a method called Diffusion with the Reformer architecture to generate amino acid sequences conditioned on a string representation of the protein backbone. This string representation, called 3DI format, follows a 20-character alphabet. Each character captures spatial information of an amino acid residue to its closest neighbor in 3D space. Part of this work also included the investigation of the distribution of the 3DI tokens within three-state secondary structure. We found that each residue displayed a tendency of more than 50% towards one of the three states. Notably, 12 out of the 20 residues even showed a significant 70% preference for a specific state. We also found an imbalance towards the V token that is found in helices in 80% of the observations, this showing an imbalance toward the helical structures. This encoded structure information is used as conditional information for the diffusion process. Diffusion models in general consist of two main processes, the forward diffusion and the reverse diffusion process, also called denoising. During the forward diffusion, the input data is sequentially destroyed by adding noise big T times. In the reverse diffusion process, a machine learning model, typically a transformer model, aims to predict the noise that was added at each time step small t, which is then removed, resulting in the reconstruction of the original data. Diffusion LM proposed to apply that diffusion processes on the continuous embedding space of discrete text input, which was picked up by Diffusion. To lead the generation of data into a desired direction, in previous works, embedded conditional information was added into the latent space of the respective model or by using additional classifiers. Diffusion, on the other hand, joins the tokenized target and source sequences together and only applies the forward diffusion process on the target embeddings. This keeps the conditional information intact. This process is called partial denoising and allows the transformer model to pay attention to the clean source embeddings while learning to remove the noise of the target embeddings. To evaluate our model, we first generate the amino acid sequences. We then predict their structures using ESMFold. We decided to use ESMFold because it is way faster than AlphaFold and has only minimal performance loss. We then apply FoldSeek to obtain the LDDT score and TM-align to calculate the RSMD, TM score, and sequence identity between the generated and reference sequence. For training the model, we used 1 million sequences from the AlphaFold database for which the 3DI tokens were generated. We redundancy reduced on sequence and structure similarity and removed sequences smaller than 30 residues and sequences where the PLDDT score was below 0.7. Due to hardware and time limitations, we truncated the sequences during training and inference to a length of 125 for now. The model performance was tested on 474 sequences, and the performance is compared to Protein MPNN, an encoder-decoder model trained on protein backbone coordinates. LucidProts achieved a median LDDT score of 0.58, a median TM score of 0.4, and a median RMSD of 3.49 angstrom, with a median sequence identity of only 0.17. These results show that we surpass random sequences in all categories. However, we do not yet reach the outstanding performance of Protein MPNN. But of course, I don't want to release you from this talk without showing you an exemplary structure alignment. In blue, you can see the predicted structure of the sequence generated by LucidProts, and in orange, the AlphaFold ground truth. This structure has an RMSD of 1.82 angstrom and an LDDT of 0.59, with a sequence identity of only 29%. And as you can see, Helical, sheet and loop structures are already aligned almost perfectly, where the disordered prefix of the sequence is pretty different, leading also to a decrease of the LDDT value, but this effect has to be investigated further. In conclusion, we first have demonstrated that each 3D-I residue has a secondary structure prevalence. Then we have shown that LucidProts gives promising results for applying diffusion language models on the inverse folding problem. However, it does not yet reach state-of-the-art sequence generation models. But because of the string representation of the conditional task, LucidProts is easily applicable to other tasks, such as generating sequences with specific functions or for designing binding partners. And this marks the end of my poster presentation. If you are interested in additional information about the model and dataset, I warmly invite you to scan the QR code, which will guide you to the GitHub repository of this project. Alternatively, feel free to contact me directly. Thank you for your attention and enjoy the rest of the conference.